Okay. Super. All right. So welcome back. Thank you to everyone who showed up at 9. I hope you all enjoyed the dinner last night. So first, before I continue on with the Relaxion, I just want to say I was very unhappy yesterday with how I presented the arguments for no global symmetries, weak gravity conjecture, and so on. I could tell that many of you were unconvinced, which is fantastic, because you shouldn't just take anything I say at face value. You should question it, and I could tell you were doing so. We don't have time to revisit it, but I would strongly recommend, there are many good references on this material, but if you look up these TASI lectures, I think they're last year by Matt Rees on, I think it's called No Global Symmetries for the Axion or something. It's on the archive. I would take a look there and take a look at the references inside. If you're interested and you don't buy what I was telling you yesterday, that's a better place to look. Okay, so we're going to continue on with the Relaxion. As I said, this is something that was proposed 10 years ago, almost 10 years ago. And it's an approach to thinking about the hierarchy problem, which is really very different to the usual symmetry-based approaches. It really, I have to say, it really energized the sort of model building community when it came out. It was a very exciting idea, largely because it was just qualitatively so different. I'm not going to go through the ingredients, the recipe for the Relaxion, which we had on the board at the end of the last lecture. If you can't recall all of it, just take a quick look at the notes. But we ended up at this Lagrangian here, where we had some new field, phi, which will be the Relaxion. And it had a shift symmetry, so you can have plenty. There's no problem with having operators like this, where you have d derivative acting on phi, and it's coupled to some operator, construct some current, not necessarily a conserved current, some current constructed out of standard model fields. That shift symmetry was broken by some spurion g. So we have terms like this. It can couple to standard model fields. It has scalar potential and so on. All of these dots involve, we're not, there are no skeletons in the closet here. We're writing down all of the terms that are allowed by the series. So they're implicitly there. And the last thing is that it had this coupling to GG joule, which I argued is essentially of this form and will not generate in perturbation theory any potential for phi. In perturbation theory, it respects the shift symmetry of phi. However, we ought to think a little bit more carefully about this term. I'm sure many of you know this because I'm sure I know for a fact that many of you have thought about axion physics. So many of you will know this, but I'm going to briefly go over essentially the axion. So if you forget this for a second, the axion solution to the strong CP problem and the material is essentially the same. So we can kill two birds with one stone. So if you think about the QCD action, this is a simplified Lagrangian where we just have the quarks. They have some mass. We're just essentially doing one flavor of quark here. And then you can have all sorts of terms. And in particular, you can have a phase in the mass. So I've got plus Hermitian conjugate here. You could write this with a gamma 5 if you were so inclined. So you could have a phase in the quark masses. And we know such phases exist because we have the CKM phase after all. Non-zero, oh, sorry, I should have had a 1 over 32 pi squared here. I'll just write it over here. We could have a non-zero a CP violating term here. This is just some phase as well, theta. And this will be, for these purposes, this will be the axion was the same as here. So the axion, relaxion, they're interchangeable at this stage. Now, what's very interesting about this term is you would think it's that this constant piece here would be unphysical, and presumably that's the reason. Who's visited CERN? Lots of people. Who's bought the T-shirt? Okay. So this is not on the T-shirt. I don't know why. The T-shirt is missing something, as are the mugs. And the reason is that you can do a partial derivative, and if this is a constant, then you would do something like this, and you've got d mu of theta, but theta is a constant, so you would get 0. So naively, you would expect that this term has no physical consequence in nature. So why would you include it? Why would you even put it on the t-shirt in the first place? But as many of you will know, things aren't so simple. And an easy way to see that things aren't so simple and that this theta term is in fact physical is to use the Carroll-Lagrangian. So we will do a field redefinition in a second. But before we do that, we will do that to calculate the axion potential. Before we will do that, can anyone tell me what physical consequence, the most famous physical consequence of this theta term would be? Yes, the neutron electric dipole moment tells you that this theta term is small. I can't remember if it's in these conventions or not, but I think in these conventions it's something like 10 to the minus 11 or less. This is something you should look up. I don't have time to go through it. But the basic argument is that you can, using essentially the field redefinition that I'm about to do, you can track how this theta term enters into the Carroll-Lagrangian. You can integrate out fields at one loop, and you see that you generate a contribution to the neutron electric dipole moment. In that way, there are various other arguments as well. But what we want to calculate is how it enters into the vacuum energy. So that is also a physical consequence of this theta term in this action. So what we'll do is a field redefinition. We will take Q goes to Q e to the I theta plus phi over f. So this depends on the field as well, the field phi. And so you'll see this will then show up in this term here. But remarkably, this symmetry, or this non-symmetry, this field transformation is anomalous. And so what it does is it shifts the coefficient of this term here. One way to think about this would be to see that you have, is to use the triangle diagram method. So you can think about inserting some phase here. This would be this field rotation. And you have a triangle anomaly. Or even nicer, is that, who's come across the Fujikawa method before? Yeah, that's very physical and a very nice way of deriving this result. And so not only does this term show up in here, but it also will show up in here, and exactly, I've picked it so that it will exactly cancel this. So once we do this field redefinition, we end up with a new action, which has the same kinetic terms. And in here we have e to the I theta q plus theta plus phi over f, q bar q plus Hermitian conjugate. We've killed off this term here, but we will also, you see in here we've done a field redefinition, so you'll pick up from the kinetic terms, for instance, derivatives acting on phi. So you will shift the form of these terms here, but they still respect the shift symmetry, so I'm going to reabsorb them into what I define to be this term here. Okay. We're taking a simplified approach here, but it will, to a large extent, also apply to full QCD with the up and down quarks, even with the strange quark, and even in the instance that the quark masses are not the same. But we're just going to take a simplified approach here. And recall that thanks to QCD, the quarks condense, and you get spontaneous chiral symmetry breaking in QCD. And so we can take a very, this is going to be a little bit sloppy, but it's fine. Recall that MQ, the VEV of MQ times Q bar Q, the quark condensation, is the parameter combination F pi squared M pi squared. And this is by definition, you can, as we discussed in the second lecture, you can derive the pion mass from this procedure. And so we can just make that replacement in here. Don't forget we've got the Hermitian conjugate, and we get the V of phi after chiral symmetry breaking is F pi squared M pi squared cosine of theta q plus phi over f. And so you see that the minimum, there's a minus here, so the minimum of this potential is at the point where all of this is 0, or any multiple of 2 pi. And so if phi is a dynamical field, then it will want to go roll down and sit at the bottom of its potential. And at the bottom of its potential, its value exactly cancels all of the CP violating phases that we started with in the theory. And so that's how the axion solves the strong CP problem. We don't have G turned on here. It's not the relaxion yet. This is just the axion. So this was a very, very beautiful idea. And in some sense, it was the first example of a mechanism by which one could understand or resolve a fine-tuning puzzle through dynamics, right? Because this field really has to be dynamical. It has to, be able to move about in the early universe and settle down at the bottom of its potential. You can also differentiate this twice at the bottom of the potential to extract the axion mass squared, because that's just the second derivative of the potential. And you'll see that it's f pi squared m pi squared over f squared, which is the usual relation you will come across. Okay, are there any questions about that? Yes? Someone's asking questions online here. No, I haven't put any gamma 5s in. You would see the gamma 5s once you do this, if you wanted to write it without a Hermitian conjugate. I don't really like gamma 5s. Anything else? Quick question. I guess in the US you call this a pop quiz. What if we didn't have the Higgs, what mass would the W boson have? Okay, that's an answer. Pardon?
Order lambda QCD.
Right, exactly. And so why is that?
Because this would also end up breaking
Yes.
very low scales.
Okay, exactly. So if you think about it, I shouldn't be doing this because I should be telling you about the hierarchy problem. But if you think about in the standard model, these operators Q, U right, for instance, this combination has the same quantum numbers. Well, the Hermitian conjugate quantum numbers as the Higgs. And so when the quarks condense, they get a VEV. That VEV is F pi. So that's a field. This combination is a field that has a VEV, F pi, which has the same quantum numbers as the Higgs, so it would generate a mass for the W and Z bosons, which is really weird. Right? I've never understood this. Why did nature want to break electroweak symmetry twice? It really did not like electroweak symmetry. We have 3 generations to have a phase that it doesn't use, and yet at the same time, it provides us with 2 mechanisms for electroweak symmetry breaking. Okay, so that is the axion and the strong CP problem in a very quick nutshell. Now we're going to go back to the relaxion, and all we do is we switch G on. Okay, the only change in the story here is that we have this explicit breaking of the shift symmetry. And so now we can sort of map out the full QCD potential. Sorry, the full relaxion potential. So this is no longer the axion, it's the relaxion. So we've got all of the, I call it VG terms. And without much loss of generality, we're not assuming that the potential is exactly linear or anything like that. That's not a special requirement. But we will assume that it's monotonic. So it's all in the range of field values that we're interested in, that it has the same gradient the whole time. So the relaxion potential would look like this. Some line like this. That's 2 straight. Okay. I can also choose what I call to be, I can always do one last shift of phi to choose what I call the origin, like phi 0 to be. That's a completely unphysical transformation. I can just do it to make my life easier. And so I will shift phi such that the point phi equals 0 corresponds to the exactly the point where it cancels, see from that second term and the first term, where it exactly cancels the Higgs mass squared. So phi equals 0 corresponds to 0 Higgs mass squared. This is not a fine-tuning of a parameter or something. What I'm doing is completely unphysical. Any calculation you do without having done that will give the exact same physical result. So it's just to make my life easy, because it helps to identify a useful point on the board. Okay, so this is what the potential looks like, but we need to now remember this piece here. And this piece here, it will be wiggly with a period of 2 pi f. And so if f is much smaller than this overall field range, we'll call this delta phi. And we'll come back to discuss delta phi. Oh, that's far too low. Sorry, I understand. Many of you won't see that. So we'll call this the whole field range from here to here, delta phi. And if f is much smaller than that field range, then these wiggles will be fast. They will enter. There will be many of them across this field range. Furthermore, this is f pi squared m pi squared, which is proportional to the quark masses. And the quark masses are proportional to the Higgs VeV. So as you go across here, say the Higgs mass squared at this point is positive. You go across, the Higgs mass squared becomes negative, 0 here, and then it becomes negative on this side. So a Higgs VeV starts to turn on. But the further you go in this direction, this is the phi direction, the further you go in this direction, the bigger the negative Higgs mass squared is. So the larger the Higgs VeV becomes. And so the coefficient of these wiggles is growing. So actually what I drew isn't strictly correct. The relaxion potential looks like this on this side, and then with wiggles that are becoming bigger and bigger as you go to the right. Is any of that unclear? Does anyone have any questions? If you don't understand it, let's not move on until you do, because this is the crucial piece. Yes? Okay, this is a great question. So how big is delta phi? How big is this field range? Yeah. I was going to come to this later, but let's just do it now. So delta phi, so what's the regime of validity of this effective field theory? That's the question we should really ask. We would say that delta phi is at least large enough to fully scan the Higgs mass squared between the two cutoff values, plus cutoff squared and minus cutoff squared. So delta phi has to be of order m squared over g. And you see this parameter combination here doesn't know anything about f. So they could, in principle, just be completely different. So f can be, and you'll see it is required to be orders and orders of magnitude smaller than delta phi. So these are fast. These are very fast wiggles. Yes?
For something regarding the mass of the Higgs and the vacuum expectation value of phi that cancel the mass of the Higgs. But are we using the shift symmetry already to remove the theta q and theta? So are we using the shift symmetry?
So this would be, it's a really good question. So the question is, haven't we already used the shift symmetry? I've not used the shift symmetry here, so you can include these theta q and so for the axion solution, you go to the bottom and it does that itself. It's not us doing an unphysical shift. It just goes to the bottom of the potential. We can leave these in, but these are of order even to cancel these off. You know where the bottom of a wiggle is of order f, which is tiny compared to this field range. So even if I did do a further shift, so that this isn't the point that m squared of the Higgs is exactly 0, and I did a shift, take that, and then I shift it a little bit more to make the minimum of the wiggle at that origin, it's not going to change this picture. That's a good question. Yep.
If the field range is this big, like, do we need to worry about higher dimension operators or EFT?
That's a great question. So the question is, for a field range of this size, do we need to worry about higher dimension operators? No, this is all consistent. So if I take any term in the overall expansion of the EFT, so everywhere I have, so a generic term will look something like m to the 4. This is being a bit sloppy. By the way, we're assuming the dimension of a potential has the dimension of mass squared and field squared. So we're assuming the UV, I probably don't even need to say this, but we're assuming the UV has some order 1 couplings in it, so that the mass and the field values are comparable. So let's call it m to the 4. We make a similar approximation when we say the potential for QCD is of order lambda QCD to the 4. This is why I'm very careful to write f pi squared, m pi squared. Potential has dimensions of vev squared, mass squared. But I'm just going to be a little bit sloppy here. Assume the UV completion has order 1 couplings. So then the height of the potential is of order m to the 4. A generic term in the potential will then look like g phi over m squared to some, let's call it n, to some integer. We'll have an infinite number of these terms in general. And if you see that if delta phi between the two extremes, delta phi is m squared over g, then this is just an order 1 number times m to the 4. So we're not, there are no bodies buried there. That's all consistent with EFT logic. Okay, these are all fantastic questions. Any other questions? Yep.
So if I recall correctly, the relaxion still has a little hierarchy problem. Can you comment on the distinction between hierarchy versus little hierarchy?
Yes, we will get there when first we have to find out if it solves any sort of hierarchy problem. So let's not jump ahead. We will get there. Yep. But are there any questions about this stuff here? Yep.
So the idea is that this theta q would be the CP breaking at low energy that we observe in the standard model, but very small. But then at higher energy, something will happen where phi will no longer be super close to theta without the.
So this is a good question. So the question is theta going to give us the CP violation we see in the standard model at low energies, and a bit more about high energies. This is all. So let's get to the mechanism. Let me show you the mechanism, and then we will see where we land. So, there are any questions about this, about the Higgs vev and this overall picture? No. Okay. Excellent. So now we have a story where we see that there could be some back reaction. And so now we need to introduce the dynamics. So the idea for the relaxion is that you would start, this isn't going to be fine-tuned, you just start with an initial field value in the early universe during inflation, which is on this side. So let's say up here. But it doesn't have to be in a special point up here. And then the relaxion field will want to roll down its potential as the universe evolves. So it will roll down the potential. Now, as you would expect in flat space, if this were by conservation of energy, this field would never get stuck in one of these wiggles unless they got, a barrier became higher than where it started, because it will just roll down and continue to roll over the wiggles because it would have lots of kinetic energy. But if this is during inflation, then there's Hubble friction on the rolling. So if this is happening during inflation, then we have to consider the equation of motion for this scalar field in the de Sitter background. And so this classical equation of motion is phi double dot squared. Sorry, phi double dot plus 3h phi dot is equal to the derivative of the potential. So gm squared plus other terms. So this is the Hubble damping. This potential, by the way, this is equation of motion. Here's a homework problem for you. If you put in just the inflationary background, e to the ht for the metric, and then solve for the equation of motion of phi, the classical equation of motion, you get this equation. You just pick up, when you're differentiating with respect to time, you pick up a differentiation of e to the Hubble t, e to the 3 Hubble t, which gives you this term here. And you can see that this is like the left-hand side is like the equation for a damped harmonic oscillator, for instance, if you had the right-hand side was an oscillator. But more generally, this is a damping term. And so, even if you start with some generic velocity for the field, some generic initial condition for the velocity and the position on the left-hand side here, it will quickly approach what you would call, I guess, is an attractor solution. Lots of different initial velocities will all lead to the same solution, which is that phi rolls at a constant speed, which scales as the velocity is gm squared over 3h. So the field value is something like phi 0, let's say, plus phi 0, the initial condition, plus this. So it rolls steadily. It's not this. You can't think of this as we would in flat space. It's not picking up kinetic energy as it rolls down. That kinetic energy is being essentially dissipated. And so it rolls at a steady value. So that means if it's rolling at a steady value, it's not getting faster and faster. It can actually get stuck. So the story for the cosmological dynamics is that it would start here and roll down, and then within, probably not the first minimum, but in one of these minima, it's going to get stuck. Okay. And we can ask then, where does it get stuck? And we can find out where it gets stuck because it will start to get stuck whenever a minima appears. So you have to have a first derivative of this potential, which is 0, telling you that there's a minimum or a maximum. And that will occur whenever we can just differentiate both sides. So this has a gradient. The G potential has a gradient of order gm squared. This potential has a gradient of order f pi squared m pi squared over f. So the first minimum will appear whenever gm squared is about the same size as f pi squared m pi squared over f. But you can recall that this is just, you can write this actually, let's write it proportionate. F pi squared m pi squared f multiplied by the quark mass over the observed. That's not a very good way of writing it. Let's just write it as f pi squared lambda v, where v is the vev of the Higgs. Let's do that. Okay, can you read that? Is that too small? No. Okay. So this is when it will stop. But phi itself determines the vev of the Higgs because phi is setting the Higgs mass squared. So once we've fixed m and f, we can have g as small as we like. And remember, g can be naturally small because it's the only spurion that breaks the shift symmetry. We can pick g to be as small as we like in order to get the place where it stops to have a Higgs vev that is as small as we like. So if g is very, very small, the Higgs vev in this solution will be very, very small. I've underlined in my notes, very clever, because it is. Are there any questions about that? Yes? Tunneling? Yes. Oh, indeed. So it can indeed tunnel, but you can check, and the lifetime is very, very long, much, much longer than the age of the universe. The reason for that is that the tunneling, the action, the bounce action, depends not only on the order lambda QCD, but also the field distance. And as we'll see in a second, the field distance is going to be enormous. And so it's very, very suppressed. This is a great question. Yep?
If I see the solution, it seems that it just continues going down and down and down. So I guess that you need the universe to go away from inflation and start radiation dominator or something like that.
So no, so it doesn't keep going down. So this was on the left-hand side without the wiggles. Sorry. Yeah, I didn't explain that clearly enough. So yeah, this is when it's rolling down here. In general, this equation on the right-hand side, you just have v prime. So that includes the wiggles.
So follow-up question.
Yep.
Does it make a difference if I solve this equation during radiation domination?
So it has to be during inflation.
Why?
Good. This is a great question. So the question is, could okay, I was a bit quick there. So the initial proposal has this evolution occurring during inflation because it makes use of the Hubble friction. Otherwise, the field would naively just keep rolling down. I'm not going to say you can't do it during radiation domination because there are related proposals that do this sort of thing during with slightly different couplings and so on that can work, I think, potentially during radiation domination. So the overall approach is, to me, it doesn't seem absolutely fundamentally tied to using inflation. But if you want to do it in a different era, you do have to modify some things. You need some particle production or something like this. Great question. Yep.
So not tunneling, but would there be any thermal hopping?
Thermal hopping, yes. Okay, great. These are all amazing questions, by the way. These are all the questions. I'm not exaggerating here. These are all the questions that people that model building, professors or whatever, at the time were asking each other at coffee time when this paper came out, and they were doing calculations to see if it worked and so on. The thermal fluctuations, can we do it during radiation domination, tunneling? All of these questions are really, really on point. Okay, so let's answer these questions. So we have to solve a bunch of conditions for this to work. And this is where things are going to get weird. The first one we've already seen, that the field range needs to scan the full natural range of the Higgs mass squared. So m squared over g. You also require that Hubble, I'll call it Hubble HI, Hubble inflation, because I've been using H for the Higgs so much. HI has to be larger than the cutoff to the squared over m Planck. The reason for that is that you will recall that Hubble squared is the potential divided by m squared. And so if Hubble was less than m squared, Hubble was less than m squared over m Planck, then actually from going to here, you would have ended inflation. You would have gone through zero vacuum energy down to anti-de Sitter. So you need all of this to be happening in an inflationary background, which means that the inflationary potential itself has to be bigger than this. Hubble also has to be less than lambda QCD, which is where I start to answer your question about sort of thermal fluctuations, in the sense that if Hubble is larger than lambda QCD, you don't actually have the wiggles. You don't get the axion potential. There are two ways of thinking about this. One of them is probably more correct than the other, but I think they're both useful. If you're you can think of Hubble as being like an effective temperature, like the Gibbons-Hawking temperature. There's a little leap of faith here, but you can think of an inflationary background as being like a background at a temperature which is Hubble, or Hubble over 2 pi or something like this. And so if you imagine QCD at temperatures above the QCD phase transition, imagine it like 10 GeV or 100 GeV, then the theory is very, very perturbative, and so non-perturbative effects are very small. Non-perturbative effects go like e to the minus 8 pi over alpha, right? And so if alpha is becoming small, that's e to the minus a large number, so non-perturbative effects are small. So, and this was entirely a non-perturbative effect, right? It required, in its entirety, on quark condensation, which is a non-perturbative effect. So if Hubble was above the QCD scale, the axion potential, the wiggles would be very, very suppressed, and they'd be too small, and you just keep rolling. Another way of seeing this, which I find more intuitive, is that Hubble is really a horizon. All the things that are physical to you and de Sitter are inside your horizon. Whatever's going on outside, for all intents and purposes, doesn't exist. But the axion potential is generated by QCD instantons. And if Hubble is above, and they have size of order the QCD scale, inverse QCD scale. And so if Hubble is above the QCD scale, your horizon isn't even big enough to fit an instanton inside it. And so those effects will be suppressed. Okay, great. The last one, which is, we'll take a little second to explain, which is related to what I just said, is that Hubble has to be less than gm squared to the third. And this is so that this is to because you want to require that the evolution of this scalar field is approximately classical. We use this classical equation of motion here. That was homework. Let's call it homework. Derive this. It's really fun. Just takes a few minutes to describe the evolution of this scalar field down the potential. But also, when you're in inflation, because you can think of this as being like a thermal background, there are fluctuations of the field. And so imagine you start here, and you're fluctuating back and forth with field fluctuations of order Hubble. So you could fluctuate up here, you could fluctuate down here. And in fact, if your fluctuations in a Hubble time, which are of order Hubble, are bigger than the distance you would have classically rolled, then this picture of the field classically rolling down is garbage, right? Because the fluctuations are so big that you're just all over the place, right? The field is bouncing all over the place. You'll just populate all of this. Or maybe we'll come back to this later, perhaps. You might even have a distribution that's peaked up here. And so to not be in that limit, you need to be in the classical regime where the classical rolling is really the dominant description, and that these Hubble fluctuations are a subleading effect. And so that leads to this, this constraint here. It's super fun as well to try and derive this for homework. You just literally compare how far you would roll in a Hubble time, so T is 1 over Hubble, to fluctuation in that time, which is of order Hubble, and you can derive this super fast. You see that this is just the gradient of the potential. So you get Hubble cubed has to be less than gm squared. Okay. You also find that you need to have enough time for all of this to happen. And so you can count time. The clock to use during inflation is Hubble, so the number of E foldings. So you need to have enough time for the field to roll the whole way down here. And so that leads to a constraint where the number of E foldings, NE, has to be greater than or equal to of order HI squared over G squared. And lastly, one that we already derived, I'll put it up here, which is that GM squared, it has to be able to stop. A minimum has to form in the first place. So GM squared F is of order or less than lambda QCD to the 4. I'm being sloppy here. This is just M pi squared, F pi squared, but everything is an order 1 estimate here. Okay, so there's a variety of different constraints that have to be satisfied for this whole thing to work in principle. Are there any questions about any of these parts? Yep. No. So in this is a good question. The question is the relaxion also the inflaton? No, in this presentation, no. So we have this constraint here really requires that the inflation is like a background. It's the scene on which this drama unfolds, but it is not playing part of the drama. There have been papers where people try to make the relaxion the inflaton as well, but it turns out it's very hard. And the reason you're about to see that this potential is extremely flat and these field displacements are extremely large, and you typically wouldn't get the observed density perturbations and so on that one would require. And so if you make the relaxion the inflaton, you also have to play other games. You have to introduce like a curvaton to get the right spectrum of density perturbations and so on. So it's simpler just to think of that as some background. Okay, so we put all of this together. And you get that you can solve. You've got enough equations here that you can solve, at least at the level of an inequality, for how big the cutoff can be. And you find that m has to be less than about m to the 4 m Planck cubed over f. Actually, no, I'll just get straight to it. Let's get straight to it. Has to be less than about 10 to the 7 GeV in units of f being 10 to the 9 GeV to the 1/6. So you see that the cutoff can't be arbitrarily large. There's actually an upper limit on how much of a hierarchy this can solve. For me, this was more than enough. I'm a bottom feeder. If I can get to 10 TeV, I can sleep at night. Some people were disappointed it couldn't go to the Planck scale. It doesn't bother me. That's subjective. G, this dimensionful shift symmetry breaking parameter, has to be around, this is for a particular choice of cutoff. I'm sort of trying to maximize the cutoff and so on here. 10 to the minus 26 GeV. Delta phi is of order 10 to the 40. This is just an example set of parameters. GeV. The number of E foldings has to be bigger than 10 to the 43. And Hubble during inflation has to be below like 0.2 GeV, but large enough that you can still have BBN. So something like 10 to the minus 4 GeV. So all of these parameters, yep. I'm glad you feel. So the comment is that, the comment was, I feel like this is not a good idea. Right, okay. Second comment was, it seems like the hierarchy problem has been transferred into having these crazy parameters. My answer to that would be no. Right, this is all playing, now it's weird, but it's all playing by the rules of effective field theory. There's been no fine-tuning of parameters here. A small number is not fine-tuned, necessarily. Right, okay, so that's the second question. So the constraints from string theory. So indeed, this is very deeply in the swampland. Normally in string theory, we even call it the distance conjecture. So within that family of weak gravity conjectures, one facet of that is that you don't expect to find field displacements, field ranges for scalar fields that are much, much greater than m Planck. So for that reason, it's deeply in the swampland. This is also, I think, probably deeply in the swampland. This is a tiny, tiny parameter. It is also saying something, in dimensionless units, divide this by the cutoff or something like this. This requires that your global symmetry, you can turn it on its head. It requires that the global symmetry is actually a very, very good global symmetry. This global symmetry parameter, breaking parameter, is very, very small. So maybe even quantum gravity would have already violated that global symmetry by more than that. So these are valid concerns. You should also be petrified by this. Yeah, it's usually 60. We're used to seeing exponents with inflation, but this is the thing in the exponent, right? So this is the number of E foldings. So yes, these are very surprising numbers. Maybe I don't, personally I don't know how how to interpret the weak gravity conjecture, type constraints, like for instance on this. There are mechanisms, there's one known as the clockwork that might evade those constraints. So I don't know how seriously to take them, but one should think about them for sure. But nonetheless, this is a first dynamical possibility for explaining a hierarchy between the electroweak scale and the cutoff, which is pretty remarkable in my view. And yes, we would have to, it would, in some sense, the fact that the parameters are so shocking is compelling to me, because the problem that it's trying to solve is so big that I would be surprised if the solution to the problem doesn't require us to rethink something dramatically. So maybe it's not so bad. A much more pertinent issue is that it's experimentally excluded. And the reason for that is that in this model as it stands, you see that the minimum, I'll just use this bit of board here, because it follows on from this. Right, for the minimum to be created, you need that V prime is 0, right, at a minimum. That's where the field will stop. But V prime is V prime of the axion part and V prime of the G potential. So I'm calling VG all the terms up here that come from the explicit symmetry breaking, plus this for the, let's call it GG joule or something like that, QCD. So this is just the cosine part. Now you solve the strong CP problem if you have this. But here, V prime G is the slope of that potential. So this here is not equal to 0 anywhere. And so for this to have a minimum in the potential, then this here has to be not equal to 0, which means that this field is not sitting at the bottom of this cosine potential. So you're unsolving the strong CP problem. You're predicting a large neutron EDM, which is why it is ruled out. One can get around this, and it's a very curious observation that when you do try and get around this, it seems that you have to, the story has to involve new states, in particular electroweak charge states at the electroweak scale. Essentially, what you do to circumvent this issue, which is the biggest one, the QCD relaxion doesn't work. That's a takeaway message. To resolve this issue, you can repeat the same exercise, but with a new gauge group, not QCD. So you have some new gauge group that condenses and creates like a new axion-like potential for your field. But the masses of the particles in that in the coefficient of that potential here, those masses have to depend on the electroweak scale. That was what the back reaction came from here. M pi is proportional to M quark, which is proportional to the Higgs FeV. And so when you extend the model to solve this issue, you inherently have to add new electroweak charged matter, and it can't be too heavy. So it's sort of curious, right? This solution is moving, or approach is moving a long way away from the symmetry-based approaches. And as I hopefully convinced you, the symmetry-based approaches seem to require new states at the TeV scale or electroweak scale or something like this. Yet, still you can't escape that, even when you go to such extremes. So maybe there's a lesson in there, a general lesson, but I'm not sure what it is. Yep.
So, it's really not low to just have this relaxed mechanism and then solve those things so that if it's really the only there are other solutions
So this is a very, very good question. So the question was, the observation is that there are other solutions to the strong CP problem than the axion. And so would it be possible to do this with the axion and use one of those solutions? Fantastic idea, write a paper. That's a really good idea. I don't know. My hunch would be that, so these would be like the sort of the Nelson bar style spontaneous CP via breaking and things like this. There are lots of neat models on the market. My hunch would be that they two don't commute, that they won't play well together, because you're really relying on the strong you're really relying on the strong CP, on the coupling of this field phi to the strong CP properties. So even if you had started with these terms 0, you started with no strong CP problem, you're still going to land at a point where this thing here is not 2 pi or 0, because the derivative of this has to be non-zero, because you're balancing it against the derivative of this, right, over here. And so my hunch would be that you can't put the two together, even for those non-axion solutions, but it's worth thinking about.
You have to build a model where little g reduces to 0.
Yeah. Yeah. I should also say, you might be able to do, okay, we're actually just doing research here now, but something you might be able to do is find a mechanism where you kill off the wiggles for phi after this happens. It just so happens that rolling is IR dominated. And so you can see that even if you turned off these wiggles and it started rolling again after reheating, that you wouldn't actually roll very far. You would still solve the electric hierarchy problem, but this field would be still rolling. So maybe I know ambience chase DESI or something at the same time, because you would have there'd be some scalar field with a very, very shallow potential that's still rolling, and in the past it had solved the electric hierarchy problem. And then maybe you could invoke some other mechanism for strong CP because you've decoupled them. I don't know. It's a very interesting question. Are there any other questions about this? Yep.
Yeah, so I guess a general question. If I write down some dark matter model, how much should I worry about whether it is in the swampland or not?
Oh, okay. So the question is, so this is not really about this. It's about the swampland. The question is, if I have a dark matter model, should I worry if it's in the swampland? It depends who you ask. Okay, I can tell you my view, but you don't have to take it any more seriously than anybody else's. My view would be, no, don't worry about it, but think about it. So don't just ignore it. If you have some model and it does some neat stuff, makes some interesting or unique experimental predictions, and it's in the swampland, then that shouldn't stop you from writing a paper or investigating that theory. But also, then you should understand that has implications for what the UV structure of nature would look like, and it would presumably not be something like string theory. That would be my interpretation. I would never see it as a roadblock, but it's certainly a signpost that you want to pay attention to, like danger or something, cliff here or something. Okay. Any other questions? So you have some options. We can talk about a thing. Okay, but I'll give you 3 options because we have about 15 minutes before I should wrap up. 3 options. A quick review of supersymmetry. I wrote some notes to fit supersymmetry into like 15 minutes last night, so in anticipation for this. A quick review of n-naturalness, which was a model that was non-dynamical in a very different way to this stuff for approaching the electroweak hierarchy problem, naturalness fine-tuning, that involves lots of copies of the standard model, many, many. It's very, very interesting. Yeah, I'm going to give you those 2 options. The other option, potential option, is a thing that I worked on called self-organized localization, but I'd rather discuss that over coffee. So, n-naturalness or Susie? Susie? Okay, well, let's take a vote. Hands up for n-naturalness. Man, it's going to be close. Okay, Susie? No. Cheating. I think it's the same. Yeah. Well, that is fine-tuning in action. Okay, let's do Susie. Out of respect for my forebears. Okay, so a quick explanation of Susie. Who has learned about supersymmetry? Okay, quite a few of you. Is supersymmetry dead?
Definitely not.
Definitely not. Yes, it is. Okay. Okay. So supersymmetry. So this is so. Okay. So the goal of these lectures was in pursuit of new paradigms, and I think both aspects there, pursuit and new paradigms, I tried to follow here. I've presented you with things that are incomplete. So that's the in pursuit. They're work in progress. And also, I've tried to lean heavily on the new paradigms, i.e. ideas, maybe they're a bit wacky, maybe not too wacky, I'm not sure, but new paradigms, so things that are sort of have been brought up relatively recently, I guess. However, I did show you the sort of canonical story for PNGB Higgs, so I think it's okay to show you supersymmetry. But supersymmetry is definitely not something that is a new paradigm, and it's not something that is even tremendously pursued for the question at hand, which is the electroweak hierarchy problem. How Susie can play a role in that is, in my view, pretty well understood. However, it is a tremendously valuable tool in theoretical physics. Right? I said that sometimes you know a theory, you know a UV completion, for instance, but you use effective field theory to identify a small parameter about which you can expand, and then you can maybe do calculations, solve problems more easily than if you just worked with the complete theory. Another way that you can solve problems approximately in particle physics, even if you know the theory that you want to study, is to find a theory that's sort of like it, which has more symmetry. And then if you study that theory that's sort of like the one that you're interested in and has more symmetry, that can help you solve problems and explore qualitative features of quantum field theories that you might not be able to in the theory that you're studying. So the example would be QCD and something like supersymmetric QCD. And so Susie still has tremendous value in theoretical physics, and it will continue to do so for many reasons. Supersymmetry is an extension of special relativity, so you should really think of it as space-time symmetry. Okay, so just for time's sake, I'm not going to write down all of the commutation relations, but essentially the algebra is defined by these commutation relations here. So you take the normal ones that you have for the Lorentz group, or for special relativity, and you extend them in here with a spinor generator. That says generator, which is fermionic. And then there is a Susie algebra, which is the following. And there are also anti-commutators involving Qs. Just for the sake of time, I'm not going to write everything down. And there are ones involving Qs and Q bars, which go like to sigma p mu, sigma u p mu. There are spinor indices here, which I'm suppressing. So one should not think of, well, I mean, I guess you can, but I really don't think you should think of supersymmetry as being like, oh, I've got an electron, so then if I add a selectron, I've got a W boson, so if I add a we know, it doesn't work like that. It starts from a very clear space-time symmetry principle. So it's not, I don't know what you might have heard people saying or reading. It's not just sort of like model builders adding particles, because that's fun. It is fun, but it really follows from a potential space-time symmetry. And then what we would have as quantum fields become promoted, they become bigger to become superfields, because when you have a symmetry, as you will know, if that symmetry is to be realized in nature, all the objects in the theory will transform under representations of that symmetry. Like you don't have a quark, you don't have sometimes two colors of quarks, right? Quarks are in fundamentals of SU3 and so on. So all the fields will be in representations of the symmetry, and a representation of supersymmetry is a superfield. And in terms of fields, the superfields contain things like scalars and fermions, or vectors and fermions. The fact that the supersymmetry has a fermionic generator means that particles of fields of different spin, differing by half integers, get paired together. For n equals 1 supersymmetry, which is the most minimal potential form of symmetry, you can do something very slick, which is that you can work in superspace. So your superfields become, let's call a superfield big phi. So at leading order, you can think, I'm going to get this wrong. I'm doing it from memory. I don't have it in my notes here. But vaguely, you can think of this as including a scalar field, and then something like a fermionic field. Let's say theta would usually be the parameter. This is a superspace coordinate. So you have your space-time coordinates and then a superspace coordinate, and then another scalar field with theta squared. This is all explained in the notes. I'm being very fast here. You're frowning. I should have a root 2?
No, the I. I don't think the I needs to be there.
Ah, okay. Happy? Good. Thanks. Okay, excellent. And then you can extract the scalar potential from a thing called a superpotential. The superpotential is like a scalar potential, but for superfields. So it's a function of the superfields. So this is a function of all of your different superfields. This is the superpotential. And just like in Lagrangian, you integrate, or in an action, you integrate the Lagrangian over space-time coordinates. For a supersymmetric action, you integrate also over SUSY coordinates, essentially, superspace. It's all very neat. And from this, you pick up all the terms that have 2 thetas. And so from this, you find that the fermion masses, I'm just telling you this just so we get there quickly enough. The fermion masses are equal to the second derivative with respect to all of the different phi i's. These are all the different superfields. The fermion masses come from the second derivative of the superpotential. The scalar masses, so as a consequence, we could write the fermion mass matrix squared, which would be m star f, let's say I, j, m, f, j, k. This would be equal to w, I, j star, w, j, k, just out of curiosity. And the scalar masses, I'll just put them in here. The scalar masses, it's called ms squared, the scalar mass matrix squared, ms squared ij. It turns out is given by d2v, where v is the scalar potential. This is just the usual expression for a scalar mass, phi I star be d phi j. But the scalar potential is just wi star. Sorry, I'm trying to go too quick. The scalar potential is the first derivative, wi star wi. So you differentiate the superpotential once and essentially square it. And you can see then that this thing here, you differentiate, the phi stars only hit this, the phi's only hit this. And so as a consequence, the scalar mass matrix squared is identical to the fermion mass matrix squared. So the scalars and fermions have equal mass. Why is this why does it, so this is all, it's very cool, there's lots of very cool things about it. Why is it relevant for naturalness in the hierarchy problem? The reason it's relevant for naturalness in the hierarchy problem is that fermions don't have a hierarchy problem, generically speaking. And that's because their masses, if you think about the electron mass, why have we not been scratching our heads about the tiny electron mass this whole lecture series? It's because there's no problem with having a small electron mass. Naturalness issues, fine-tuning, hierarchy problem, all of those adjectives, they do not apply to small numbers. Small numbers are not a problem if those small numbers are protected by a symmetry. It's when the small numbers are not protected by a symmetry that you have an issue. And the electron has a symmetry. If we look at the electron mass, it's me, E bar E. And this parameter here you can think of as being, if we worked in terms of left and right coordinates, we would call it like E left, E right, E left, C, E right in terms of Weyl spinners. And I have a symmetry where I can, this is invariant under something that in this case is just proportional to hypercharge, where I can rotate this by a phase and this by the opposite phase, and then the whole thing is invariant. But I could have had a symmetry, if I had no electron mass, I could have had a symmetry that, for instance, ELC goes to e to the I theta ELC, and E right goes to e to the I theta E right. Sorry for all the e's, that's horrific. These are electrons, and that's the exponential. But the kinetic terms for E left and E right are invariant under this symmetry. So this fermion mass, the electron mass, is the only parameter in the theory, or the electron Yukawa equivalently, is the only parameter in the theory that breaks the electron chiral this chiral symmetry. And so it's protected by a symmetry. So if in the UV, my theory respects this chiral symmetry, and this is the only parameter, then all the breaking of the symmetry, i.e. anything that can generate a correction to the electron mass, has to be proportional to the electron mass itself. So it can be arbitrarily small, and it's not an issue. So fermions don't have naturalness issues, generically speaking. But here, you see that this, and scalars typically do, if they have, unless they have some symmetry, like a shift symmetry or something like this. But you see here that in supersymmetry, the scalar masses are equal to the fermion masses. So essentially, the way to think about it is that the scalar sort of hitchhikes with the, with the fermion. It comes along, gets carried along, and gets to enjoy the chiral symmetry of the fermion as a result of supersymmetry. And that's why you don't generically have, in supersymmetry, naturalness issues with scalar masses. However, we have seen that supersymmetry predicts that the scalars and fermions have the same masses, but we have not yet seen, for instance, this electron. So supersymmetry must be broken. And if supersymmetry is broken, then the more it's broken, the less protection the scalars have from their partner fermions. And so one way of introducing SUSY breaking, well, if SUSY is broken, this would generically occur, is that you would have what we call soft masses. So additional terms that show up, we don't put them in by hand. That's not the approach. Supersymmetry would be spontaneously broken at some high energy scale, and this would lead to the generation of soft masses that would make corrections to, for instance, particles like the Stopes quark mass and so on. But the bigger these soft masses are, the less protection there is from supersymmetry, and so you generically get corrections to the Higgs mass squared, which look like this. 3 lambda top squared, the thing you've seen so many times before. 4 pi squared m stop squared times some log that is a ratio of scales. You can think of it as being going from the UV scale where the supersymmetry breaking occurs down to, for instance, the electroweak scale, let's call it MW. And so you get the same problem. So we haven't seen the superpartners, so supersymmetry must be broken. It might exist at very high energies, though. If supersymmetry is broken at low energies, we call that soft breaking. And that can increase the masses of, that could explain the non-observation of the superpartners of the standard model fields. But the more of an explanation we have for that, the more we have to start fine-tuning the Higgs potential again. So it's like very much similar to the PNGB Higgs story. And in fact, you can quantify this fine-tuning in the same way as the homework exercise from the other day. And it's actually it's a bit more severe, only a little bit. But at present, direct searches for the stop squarks, they're the leading characters in this story, put them at above about 1.2 TeV or more. I have up-to-date limits in the online notes. You can check them out. And so we find that generically now, of course, you or other people can debate with me the precise numbers here. I wouldn't take them tremendously seriously, but certainly within a factor of a few, I would take them seriously. This is how the tuning scales. And so at the present time, it looks like SUSY, at least in its most minimal form, is fine-tuned to like the 1%-ish level. We can calculate the fine-tuning because SUSY is a UV completion where, in principle, the Higgs mass and VEV are calculable. And as I said, we shouldn't take, it's not that 1% is bad, we throw it in the bin, 5% is fine. We use these arguments to try and estimate how plausible it is that such a theory is the UV completion of the standard model. And so it's starting to look less plausible. There's no, it's like Schrodinger's SUSY, it's never dead or alive. It's always in a superposition. And so I wouldn't say either way. It's not a binary thing. But we use these estimates to make guesses about what's going on in the UV. And this would suggest that our guess, the probability we would assign to that possibility is decreasing as the LHC continues to not see superpartners. It also reveals a very interesting interplay because you will recall for PNGB models, a big source of tension was actually precision Higgs coupling measurements. Those were the things that were really the thorn in the side of PNGB Higgs models. Here, that's also true to a certain extent, but also the direct searches for colored particles is putting pressure on as well. That's also sort of true for PNGB Higgs models and the colored top partners, but there's more wiggle room there. Okay, so I should conclude. So I guess in these lectures, I've attempted to try and provoke you into thinking seriously about fine-tuning, naturalness, the hierarchy problem. It's something that I think you should have an opinion on for yourself, and you do, right? You've asked some amazing questions, and after the lectures, you've asked some very provocative questions as well, which is fantastic. You guys should really take responsibility for forming your own view on how seriously one should think about these things, whether it's an interesting problem or there are other interesting problems. In your mind, when someone mentions the hierarchy problem, you shouldn't say to yourself, well, my supervisor is very famous and he says it's not a problem, or, well, my supervisor is very famous and she says it's the most important problem to think about. It should be really your opinion, and I'm glad to see that I think that is the case for you guys. Even if you don't think it's the most important problem to try and solve in particle physics, we do have many, which is a wonderful situation to be in. It's clear that necessity is the mother of creation, and it's clear that thinking about this problem and related problems has driven an enormous amount of creativity in theoretical physics. Right? There's a huge number of amazing ideas have been born out of thinking about this problem, and they continue to be so. So keep an eye on it. And if you do think about it, try and be creative and come up with new ideas. Also, naturalness questions have driven, as you can see here, interesting new connections between disparate fields, right? This is, this relaxion proposal, for instance, is really making a deep connection between cosmology and the early universe, and problems about the UV completion of the standard model, which is really remarkable. Okay, and so I guess that's it. I knew that when I came here and looked out into the room on the first lecture that I would be looking at the future of particle physics, theoretical particle physics, and I have to say I think it's in fantastic hands. So thanks for listening, and I'm always happy to take questions today. I leave tomorrow morning, but if you want to email me, I'm happy to arrange a Zoom or anything like that if you would like to discuss physics further. Thanks.